Live from Loyola campus of Concordia University. Wow.
That was smooth.
Loyola campus of Concordia
like
University. This is Cued for Thought on 1690 CJLO AM. And if you're listening to this, you probably own a pocket protector.
Ooh. That's...
Tough crowd. Someone at home laughed, I hope so.
I don't know. I hope so.
You know what a pocket protector is?
I do.
All right. Come on, it's funny.
I'll give you a laugh.
We're really nerding it up today because today our topic is
space.
Yeah. But you can't hear
resist.
sounds in space. So it's
nice.
Yeah.
Well done.
Yeah, that's the topic of today. I want to start you. Oh, actually, first I'll introduce my beautiful co-host once again.
Thank you.
Nate. And I must say, is that a new tattoo? It's like it's a butterfly flying over a rainbow. It's gorgeous.
You know, I take pride in the way I look. I wish there was some way that we could broadcast like images, you know, instead of just sound.
Maybe I'll put a picture on the website.
I wouldn't know what. Oh, do that.
It's glorious. Glorious.
Thank you.
All right.
Thank you, Richie.
So yeah, I'm with Nate and I'm Richie, and our topic is space. And I want to start you guys off with something. It's kind of depressing, but it's important. The universe, while it's been pretty hospitable to us for a while, the truth is it really wants to kill us. And in a few billion years, we're dead no matter what, pretty much. There's three major reasons why that's true. First of all, you might have heard that the sun is expanding. Well, it's not expanding right now, but it will start expanding eventually.
I think we've got some time there.
Yeah, we got about 5 billion years, but the clock is ticking. So the sun, according to estimates, was born about 5 million years ago. Our sun from our solar system.
Billion.
Yeah, billion.
Yeah.
I said billion.
Oh.
With a B. Sorry. We have an astrophysicist in the house, by the way. He's going to talk later to us about some
Yeah, we were
cool
going to
space
introduce
stuff.
him later, but
But
he
he just
like
had
he
to.
needed to say something.
It's billion with a B. It's billion with a B. So, yeah, the sun was born about 5 billion years ago, and it's going to live an estimated another 5 billion years. And in the core of our sun, there's fusion, nuclear fusion, thermonuclear fusion, right? And it's converting hydrogen to helium, and it's emitting energy. And at the same time, the sun's own gravity wants it to collapse onto itself. But right now, there's a sort of balance between the energy emitted by the fusion and the gravitational pull inwards. But eventually, the core of the sun is going to exhaust all its hydrogen, and only helium will remain in the sun. And it's going to want to fuse the helium as it did the hydrogen, but it won't have enough energy. So it will start to collapse into itself until it has enough energy to fuse the helium into carbon. And once it starts doing that, it'll emit more energy than it did when it was fusing the hydrogen. And it's going to start expanding and expanding. And soon it will start to engulf the planets closest to it. And that means first Mercury, then Venus, then Earth. And then we're going to bake like potatoes if anyone from humanities remains.
Should we be worried?
Yeah.
Not really.
Well, the truth is, if you start moving out to more distant planets, if we're capable at that time, hopefully, or to, I think, comets that are sort of in the area, you can sort of hijack a comet, and if you could live there, then you could postpone your inevitable death. But the thing is, even if you were to survive that, what would happen next around that same time is we're on a collision course with the nearby Andromeda Galaxy. And that's going to happen around the same time. The Andromeda Galaxy is the one nearest to our own, and it's moving toward us at about 100 kilometers per second. And it's going to take about 5 to 7 billion years to close the gap, which is around the same time as the sun starting to expand. So the truth is there's a lot of empty space. So when they move closer to each other, there's not going to be a lot of planet-on-planet collisions. But I guess the biggest worry is to get pulled into the gravitational pull of another bigger star. So we'd lose connection to our sun. And we're already in a sort of perfect distance from our sun, and it's keeping us alive right now. But if we get pulled maybe too close to another sun or get sort of like a slingshot into space, this planet will not be habitable anymore, and we're gonna have to get out of here. So yeah,
I think for a small time, the view of the night sky would be pretty cool.
Yeah,
right. See a whole galaxy pretty close.
But I was just thinking,
I'd
like,
be into that.
The sun starts expanding. You gather up all the people left on Earth. You move to a more distant planet. Then, like, oh crap, the Andromeda galaxy's right there. You have a whole other problem to worry about. And furthermore, the cosmos is expanding. And I guess we'll get more into that later. But as it expands, the overall energy remaining in the galaxy, the average temperature of the galaxy is going to decrease. And it's going to get colder and colder. And eventually there's going to be no more gas clouds to collide and produce stars. And I guess all the heat goes away.
I think that's called the heat death of the universe.
Exactly,
right?
The heat death of the cosmos. And any process that requires energy here on Earth for us to survive would pretty much cease because there's no energy left. And I know that might violate one of Newton's laws. Is it Newton's laws that said that energy conserves itself? I think it's a Newtonian law.
No, it's came later. It's an independent law. I think partly James Maxwell and Boltzmann. It's conservation of energy. But that doesn't, for the expansion of the universe as a whole, violates conservation of the energy. And some energy is created and lost as that happens.
Oh, okay, so we are losing energy over time. Mm-hmm. And the universe is getting colder. And processes that require energy are going to stop. And it's going to be a bad time for everyone. So yeah, the universe pretty much wants to kill us eventually. It's going to take a long time. And you probably shouldn't have to worry about it right now. But the truth is, humanity is pretty much doomed eventually. Do you guys have any comments on that?
Do you? You look like you want to say something.
You're sounding very gloomy. It's a very gloomy way to start a show.
I know.
The universe is habitable now, and the Earth is going to be very habitable for a long time unless humanity screws it up, which is possible, but not necessarily the case. And though the sun will get hotter, it'll get progressively hotter over the next 5 billion years, and eventually the Earth will be a scorched wasteland. It could be that within the next couple billion years, we'll have the ability to move to a different star, to a planet around a different star. Right now, that would be impossible to do, but we're so technologically advanced compared to where we were 1,000 years ago that who knows where we'll be in 10,000 years. I think if we saw those people from 10,000 years in the future, we probably wouldn't even recognize them.
Yeah, and a lot of evolution can go on. Maybe we'll evolve to survive in hotter temperatures. Who knows?
I don't know. I think expansion of the sun is like a serious deal. I don't know if you can evolve to live in a sun.
Not in a sun, but
we're 70% water, right? So
yeah, water's not going to evolve.
Start to evaporate.
Yeah.
But I have a question that I couldn't really figure out in my research. How fast would the sun be expanding, do you think?
So it expands at different rates at different times in its life. Right now, it's expanding at a very, very slow rate that I think in about 5 billion years, it'll be approximately, maybe more like 4 billion years, it'll be like 40 or 50% larger. So that's an extremely small rate,
Yeah.
right? And then after that, slow rate, sorry, not small. And then after that, it'll expand much faster. It'll grow by a factor of 1,000 in size over the 400 or 500 million years after that, which again is very slow, if you want to say it, but it'll appear to be somewhat fast to whoever might still be around then.
Yeah, if they're still astrophysicists at that time. Okay, I think we're going to take a quick break, and when we come back, we'll explain who was just talking to you.
Okay. Thanks very much. You're listening to Cued for Thought on CJLO 1690.
Slip, slide, dip and take a dive. Planets looking high when we traveling on a vibe. Cribs, dorms, grasshoppers and swarms. Thinking life is big, is that hip, is it norm? Psychedelic and fat. Flowers and beads and pieces and naps. Ah, yes, planets got the blessed. Beats are played on Friday to get Monday off your chest. Kick live, dig into the quotes.
welcome back. You're listening to Queued for Thought on CJLO 1690. And today we're really lucky to have David Nataf with us, who is a postdoctoral fellow at the Australia National University in astrophysics. Hello.
Yes. Hello, Nate.
So I have a couple questions for you. It's not every day that we get to talk to an astrophysicist. So I guess, first off, why study astrophysics?
It's an interesting field within which there's been a lot of developments in the past few decades. I got interested in it as a kid because there were pretty pictures of planets, which might not be the most relevant thing right now, but anything to set a spark, really.
Okay.
And in terms of what's going on right now, we found out about dark matter and dark energy in the past 25 years approximately. Those are important discoveries which still haven't been explained, and they'll be a big deal when we can explain them and can understand what's going on. It's kind of like, it's equivalent to the discovery of the electron and the proton 100 years ago. And also, we're characterizing planets better. So we used to only know about planets around the sun, and then we had no idea about planets around other stars. It was just science fiction. And now we're starting to figure things out, and we're closing in on important questions like how common are Earth-like planets out there. And then once we get that question, we can make it more precise, not just ask, about planets that are rocky and orbit a star once per year, but what their chemistry is. Are they like Earth or like Mars, like Venus or something else? And then eventually, how much life there might be in the universe. So in terms of why studying astrophysics, I'd say the progress has been very good in the past 25 years and should continue to be good in the near future.
Cool.
Wait, so you grew up in Montreal.
Yes.
So when you looked up at the stars, you didn't see much, I guess, if you're in the city.
No.
Do you find that most people, like in your fields, grew up in the country or places where stars are more visible?
No, I don't think that comes into play that much. Most people grew up in cities, but I think in the field grew up in cities, but I think that's just because most people grew up in cities. And they might get into astronomy for similar reasons. Just they saw pretty pictures of planets, or they read a lot of science fiction, or they think black holes are cool, for example.
All right.
Right. So I want to get to some of the things that you had mentioned, like dark matter and dark energy. But first, I was wondering if you could maybe give us a layman's explanation of the research that you do. I went online. I tried to read some of your papers. Not going to lie, they were quite dense and hard for me to read.
Well, sorry about that.
Don't apologize.
So in terms of what I do a few different things, but the overall main focus is I try to figure out the nature of the stars in the center of our galaxy. Our galaxy is the Milky Way. It's about 100,000 light years across, and and it's kind of shaped like a disk. You could think of it as a big pancake. It's 100 times wider than it is tall. And in the center, there's like a big ball, which is called a bulge. And it is believed that those stars formed first, that they're older, and they have a slightly different chemistry than the stars nearby. And I try and figure out the nature of those stars more precisely. What we have is a vague picture. They're about twice as old as the sun. I'd like to know that more precisely. I'd like to know how they're distributed in space. Is it just a sphere, or is it an ellipsoid with an angle? How fast they're moving, and what their precise chemistry is.
Cool. So what's the process? If you're looking at a star from here, I assume all we can see is their light.
Yes.
Right? And their light from a long time ago.
Yeah.
So with only that information, how do you then go and look at their chemistry? How can you assess their age?
All right. So you mentioned that it's their light a long time ago. From the center of the galaxy, it's about 25,000 years ago,
okay,
which we can approximate as being zero, because the lifetime of a star, like the sun, for example, which is it's fairly typical star, is 10 billion years. So in 25,000 years, things change very, very little.
Right.
And the amount by which they change is smaller than the errors from multiple other things. So you mentioned that we look at their light. That's true. There's many different kinds of light, infrared light, optical light, near ultraviolet light, etc. And even within those different terms or subdivisions. And each of those, you could call them band passes. They tell us very different things. Ultraviolet light tells us about the presence of young stars. It comes primarily from young stars. Optical light it actually comes from nearly all stars, like the sun. It's no coincidence that our eyes evolved to see those kinds of light rays. And infrared light tends to come from more evolved stars that are almost dead. So the sun in 5 billion years, as was mentioned, it'll become a red giant. Then it'll be red rather than yellow, and it'll have much more light in the infrared as an extension of that. Further beyond that, there's something called a spectrum of a star. Now, what I just told you is kind of macroscopic,
Okay.
but if you look at the light details, at the very fine details, an emission spectrum from a star, though it emits at nearly all wavelengths of light, some wavelengths tend to be absorbed because there's a lot of atoms in the atmospheres of stars and sometimes molecules, and that creates features in the spectrum which allows us to tell about some of the chemistry of stars. So iron and calcium, for example, those two elements make a lot of lines, and it's fairly straightforward to measure their abundances in stars.
Wow.
Yeah.
That's really interesting.
Yeah, I always wondered about that, how people sort of say things about the chemical components of distant objects, and like how can you possibly measure that without sending a probe or that sort of thing? Like in Mars right now, they sent the Mars rover to sort of investigate more detailed chemical components of the soil there, but like to do that with a telescope seems counterintuitive.
Yeah, so you can get all sorts of light from nearly every particle, but every atom and every molecule in the universe has very specific energies associated to that particular atom and molecule. And since we can measure a lot of energies in the lab, so for example with calcium, we know that there's 3 energy transitions near a wavelength of light corresponding to 850 nanometers. There's 3 energy transitions right there. And then if you could see those transitions in the spectra, such that light from stars tends to be fainter at those exact wavelengths because it's absorbed by calcium, you could then measure approximately how much calcium is in the star's atmosphere.
Wow.
Yeah.
Cool.
Dude. I think there should be a service where stoners can sort of call up an astrophysicist and rent him, like while they're smoking, and you could just sit next to them and talk like that.
So what does your work sort of suggest about the way galaxies form or evolve, if anything? It just sounds like it might.
So for this galaxy, it's a bit confusing what my work suggests, because what I have found and what a few other people doing related things have found in the past 10 years is that the history of the galaxy is not exactly as expected from simulations of how galaxies form. Okay. The picture that people had 20 years ago, or more like 10 years ago, from computer simulations, is that a galaxy like the Milky Way would have formed from the accretion of maybe like 100 or 200 similarly sized small galaxies. But it looks like that's not quite right. It looks like most of the mass of gas and stars was already there 10 billion years ago, which is earlier than expected. And there was already a smooth disk, which is again earlier than expected. And there would have been fewer mergers that would have been significant. So though there still would have been mergers, they would have been of systems that are 100 times less massive than the Milky Way, as opposed to 5 times less massive. There's been no big merger in the past 10 billion years or so, which is a surprise. And the way we know that is that if there is a violent merger in the recent history of the galaxy, it would create a lot of chaos in the orbits. But actually what we see is that the orbital distribution of stars is, as far as we can tell, it's super smooth. And because it's smooth and ordered, it implies there hasn't been much chaos due to mergers and other factors like that.
That's really interesting.
I actually looked up when I was studying about the Andromeda galaxy collision. There's a computer simulation of it on YouTube. It's pretty cool. They sort of get together and they're like swirling like a toilet. And eventually they become one. It's cool.
So this year we saw a major scientific breakthrough, which was the discovery of the Higgs boson. And I want to know, as an astrophysicist, how has its discovery changed either your work or the community in which you're working?
The best part of the Higgs boson discovery is, first of all, it's very satisfactory to see it because it was predicted approximately 30 years ago, and it's kind of necessary for a lot of the rest of particle physics to work. If it hadn't been observed, then a lot of stuff would have been thrown in the garbage. And then in order to measure it, it's such a fine thing, they had to build this really complicated accelerator in Switzerland, at the Switzerland-France border, to get it to work. It took like 10 or 15 years to construct it, a lot of calibration. There's 3,000 people working together. So the discovery and measurement of the Higgs, I see it as a good confirmation of the general scientific process, because it was necessary to be there, and then it was hard to observe, and then everything worked. It's very satisfying to see. In terms of impact on the work I do, I would say it's not quite significant, because the work I do is at a different energy level. And so things that are smaller than atoms, like the Higgs boson or the W bosons, is just at a different level. It's kind of, it impacts my work the way it might impact, say, hurricane or tornado studies in that sense. It's kind of assumed it's at a different layer of physics.
Okay.
I like to say I work at a different energy level from other people.
Yes.
Pretty satisfying to say.
So there's something that comes up in, I guess, pop culture when people are thinking of astrophysics, and it's a theory that a lot of people know very little about, and that's M theory, or theories that incorporate a multiverse.
Mm-hmm.
And I wanted to know, what do you know about multiverse theories, and do you think we're living in a multiverse? And if so, should we care? What does that do for us?
So I know somewhat about multiverse theories. Just to give a definition for the audience, the universe, it can be defined as everything that we can see, sort of, or that we could ever see if we had perfect instruments. It includes those things that we can't see yet, but that we might be able to see one day with better instruments. And so the multiverse is just the idea that there's many different versions of it, but even if you accept that there's things beyond that are further away than anything we can see, then already you believe in a multiverse. And that, to me, it doesn't impact anything I do because I'll never interact with those things, but I'm willing to believe that there's things further away than anything we can see. Then there's different layers of the multiverse beyond that, which is not only that there are other universes, but that those other universes might have different laws of physics. That could be, I'm not sure. Or perhaps that every time we make a decision in life, which also implies to whether or not a particle that's moving randomly goes left or right, then the universe splits into two and we get another universe. That's another idea. So those multiverse interpretations I find more speculative.
Okay.
I think it would be best if there's a small number of people thinking about these things, because on the one hand, it doesn't seem very applicable, which is why you might think, let's not spend any time on this. But on the other hand, a lot of things that at first seem not really relevant and come off as pure speculation can sometimes emerge later on to be a really big deal. And so if there's a small number of people thinking about it, or even a moderate number of people thinking about it, there could be something that comes out of it.
Is there anyone working sort of under the assumption that there is more than one universe?
Some people are working under that assumption. There's a lot of... It's popular. The anthropic principle is kind of related to that. And that relates to the fact that there's a lot of numbers in nature which just appear to be totally random number. Like the energy density of empty space. It has a number which is not zero, but is very, very close to zero, right? Just like extremely close to zero, such that you would never need to worry about it on Earth. And then why is it that number? Nobody knows. And then some people are tempted to say that it could be any number, and over zillions of universes, every single number is achieved at least sometimes, and we just happen to live in a universe where it takes on this value, and so on for every single other fundamental constant.
Okay.
Yeah.
So we're going to take a quick break, and we're going to get back to the second half of the interview when we come back. You're listening to CJLO 1690.
Everything is good and brown. the sunshine smile upon my face, my friends are close at hand, and all my inhibitions have disappeared without a trace. I'm glad.
The old prince still lived at home. Yeah. 1, 2, 3. Yo, I live at home still, not paying phone bills, hydro or rent, and my mom makes most meals. So it's so ill, I don't need no skrill, only cash for gas when I borrow my folks' wheels. But you can't drive. Whatever, our van died. Get a good bite. Man, who I look like, that Lance guy?
Hi, welcome back. Would you mind going over what you had just said, maybe elaborating on that?
Yeah, so there's further motivation for the multiverse idea and these speculations about fundamental numbers in nature that I brought up. Is that so we have all these numbers that particle physicists and astrophysicists measure about nature, and until we have an explanation for them, they seem kind of weird. But one thing that is noticeable about them so far is that a lot of them seem uniquely calibrated to allow for the existence of life. So, for example, the masses of the quarks, which are these fundamental particles, they're such that stars produce both carbon and oxygen. And if that wasn't the case, we wouldn't have life. In particular, carbon is important for the existence of life because it's an atom that can make a lot of strong bonds. I think only after carbon, silicon can kind of do it, but it can make as many complicated bonds, but those bonds are weaker. And for example, if the laws of physics were just slightly different, as in the fundamental numbers of nature were slightly different, then stars would make almost no carbon. They'd only make oxygen. And then chemistry would be a lot simpler in the universe, and something complicated like life could not emerge. And that's just one example. And for nearly every single fundamental number in nature, you can see that if it changed by a tiny little bit, there'd still be life. But over the whole range of values it could take between minus infinity and positive infinity, let's say, the universe would not be habitable. It would just be a boring place with nothing happening. And that's peculiar, and it makes people wonder where these numbers come from. And one speculation is that every single value for these numbers does happen, and then most universes are boring. And then small enough fraction of universes are less boring, like this one.
Is there one where people wear shoes on their hands and gloves on their feet?
I don't know.
Well, if there's an infinite number, there must be one, right?
Well, infinity is kind of weird, right? So just this is my favorite example of infinity. Let's go through all the even numbers: 2, 4, 6, 8, etc. There's an infinite number of numbers, right?
Yeah.
And you never have an odd number.
Right.
So just because you have an infinite number of something doesn't mean you achieve everything.
Oh, you just blew my mind.
Yeah.
That was cool. Thank you. So I want to get into, I guess, the meat of the interview and something I'm really excited about related to astrophysics, and that's dark energy and dark matter.
Mm-hmm.
These are, like you said, huge discoveries that are changing the way people look at astrophysics, and I guess laymen who know something about it look at the universe. And I want to get your opinion on how that's affected your work, and maybe if you could give a layman's explanation about what the two are.
All right, so they're somewhat different things. So dark matter, I'll explain first. It's that it seems, if you look at the orbits of stars around galaxies, any galaxy, in the inner parts of galaxies, there's a lot of light, and as you move out, stars keep orbiting fast, which makes sense because there's more and more stuff inside them. And then as you move beyond the galaxy, where there's just a very small number of stars, the orbits of stars should be slowing down because there's no more light, yet the stars keep on moving really fast. And for them to move as fast at a much larger distance with the same amount of light, it means that there has to be an additional... It either means two things, and the one explanation that's preferred is that there's an additional source of mass that contributes to the mass of the system of that galaxy, and thus to the rotational speeds of the stars, but doesn't contribute any light. Hence the term dark matter. It's matter contributes mass, but no light. Either that, or the theory of gravity is incorrect. That's another possibility. That's an alternative to dark matter.
Okay, so two questions about that. First being, if you could theoretically shine a light on dark matter, would you see it?
The most likely reason it's dark is that it simply doesn't interact with photons, and photons are the light particle.
Right.
So matter interacts with photons because we're made of electrons and protons, and electrons and protons each have a charge. Even though we're overall neutral, there are little charges once you zoom in on people and things, and that interacts with photons because photons are electromagnetic waves. Dark matter, if it has no charge at all, then it won't interact with photons, and then you wouldn't see dark matter.
I guess the second is you'd mentioned the theory of gravity, and that theory, as far as I know, is posing a sort of problem in that we haven't been able to sort of merge the theory of gravity with, I guess, the standard model of physics. And I wanted to know, are there theories behind that problem?
There's a lot of theories behind that problem. It's hard to tell which of them are correct. The general idea is that the other forces in physics, to give some explanation in there, which are the electromagnetic force, the weak force, and nuclear force, as of the 60s and 70s, physicists have been able to come up with a single explanation for all three of those forces, and that's called the standard model of particle physics, and it includes the Higgs boson. Gravity is a separate theory. It's from Albert Einstein and David Hilbert, called the general theory of relativity. And right now, those two are completely separate. That doesn't matter on Earth, but in situations like black holes, they predict different things, and you can't predict different things. Only one thing has to be true, which means that at some limit, one of the theories is wrong and the other is right. And it's hard to tell where that would be. And we know where it's not, and it's probably not at energy scales probed from experiments on Earth, because we haven't seen any contradictions between gravity and other physics on Earth-based experiments. So it's at a much higher energy scale, and because we can't probe it, we can't probe it as far as we know right now, which makes us more dependent on pure theory, which is a difficult way to do scientific research.
Okay, thank you. And so what can you tell us about dark energy? From what I understand, it's the universe is expanding, and it should, I guess, theoretically start slowing down and eventually contracting. And the rate of expansion should decelerate. But what's being observed is that it isn't, and it's actually accelerating. And dark energy is, as far as I know, a theory that sort of accounts for that. Is that true? And what else can you tell us about it?
Dark energy is more of an explanation than theory. Like with dark matter, a nebulous name is given to a concept, which indicates that we don't actually know what's going on. So the empty space expands because there's a very small positive energy to empty space, which causes it to expand. It's extremely small, but because the entire universe is big, it's small multiplied by big, which adds up to 70% of the energy of the universe, approximately. And nobody's sure exactly what that small energy is. If you try and predict it using very simple physics, sort of guess of what it might be, you get a completely wrong answer. And the answer is wrong by a factor of 10 with 100 zeros following it. And so it's weird that there's an energy to empty space. And given that there's an energy to empty space, it's weird that it's a number that's so close to zero but isn't zero. And dark energy is just, it describes what that energy is. Well, it states that there is energy, but we call it dark because there's no understanding of exactly what's going on.
So it's just filling in the gaps.
Yeah, it's one day there's going to be a better name once when a better explanation emerges.
So are there theories behind what that could possibly be?
There's some theories. I haven't seen any that's convincing, but
okay.
It could be that since there's so many of them, I don't read most of them. And
I have a theory.
It's a long... Yeah, what's your theory, Rich?
You put me on the spot now. I have a few papers written about it, so you can look those up.
And so you called the discovery of dark energy and dark matter, I guess you drew the comparison between the discovery of the proton and the electron. And so how are they as important for astrophysics?
So it turns out now that what we know of as regular matter, protons, electrons, and neutrons, and light, is about 4% of all the energy in the universe. And dark matter is about 20 something percent, and dark energy is the rest of about 70%. And so it's important because it's a huge mass fraction of the universe. It's a whole other sector of physics that we don't actually know what's going on in there, and it's something to be explained further on in history. What its long-term impact might be, I can't say, but if you asked somebody 100 years ago what the long-term impact of the electron would be, they'd have no idea about computers, for example. So it turned out pretty well.
Okay.
Yeah.
I like computers.
Yeah, I'm a big fan. So I have to ask, do you think it's likely that there is life outside of Earth?
I think it's extremely likely that there's life outside of Earth. The sun is a very typical star, so it's at a very typical place in the galaxy. It has a very typical chemistry. It has it's a bit younger, but that's okay. And there's like several 100 billion stars in the galaxy. About 300 billion was the number I saw most recently. And so if each time you say, well, you might say only about 10% of stars have a mass like the sun. Okay, so 300 billion becomes 30 billion. And then you might say only 10% of stars have a chemistry like the sun, which is necessary for life. Okay, so then 30 billion becomes 3 billion. And then you'd say only half of stars have lived long enough for life to evolve. So then 3 billion becomes 1.5 billion. It's still a very big number, right? And we're now finding out that most stars have planets. So then you're left with hundreds of millions. And even if you shrink it further, this is just one galaxy. It's a very typical galaxy. And there's about 200 billion galaxies like it in the universe, right? So it's basically you're rolling the dice many, many times. One thing which does interest me about the origin of life on Earth, so the Earth itself is 4.5 billion years old, and we know that life formed in the first billion years on Earth. And we can't say too much because it's just a single example, so we have to be careful about not getting our statistics wrong. But basically, life emerged very rapidly on Earth. It didn't take a huge amount of time. It's 1 billion years out of a total lifetime of 10 billion years, approximately. And so that would indicate that it happens kind of naturally. Well, not naturally, but it happens more frequently.
Right. I know that Stephen Hawking made the assertion that in the search for planets that might have life, limiting the search to only planets that are like Earth is sort of silly because that's only one type of life. I want to know if you have a comment on that.
It's a good comment. It does depend on what kind of life we're interested in. But for that, I'd respond that the technology we have now, though it's much better than what we have 20 years ago, it's still extremely primitive. And we're basically searching for whatever planets we could find without really discriminating for Earths. And Earths are relatively hard to find. The easiest thing to observe is something the mass of Jupiter that orbits right next to its star. And Earth is, I think it's 300 times less massive than Jupiter. It's 10 times smaller. And because of how far away we are from our star, we have a very small effect on our star. And so planets like Earth are, for now, somewhat hard to observe. And so astronomers are just studying whatever planets they can for the time being. And eventually, once we have better equipment, then we could start thinking about the issues of more precisely about which kind of life to target. We're not at the level now where we can measure life. We can only measure planet populations approximately.
Cool. And so one more question before we take a break and then get to our quizzes is, what do you think of lunar exploration? Is there still a point of going to the moon? And if so, what would we do there?
There's a few points of going to the moon. I think it's a good idea. First, if we want to go elsewhere in the solar system, it might be better to build our, you could call them airports on the moon, so that you'd need like a small amount of fuel to get from Earth to the moon. And then you could load up on the moon where there's less gravity and less atmosphere and take off from there. that'd be relatively energy efficient. That's one. Two, there's a lot of scientific experiments that could be done on the moon that are hard to do on Earth. For example, on Earth, radio astronomy is really hard because there's radio waves everywhere due to everything from cell phones to radio shows. And if you put a telescope on the back of the moon for radio, for example, it would see things that cannot be observed from Earth. That's also true of neutrino telescopes. Neutrino astronomy is hard from Earth because cosmic rays interact with the atmosphere, and then they create a huge background of neutrinos. And on the moon, that would be less of an issue. Also, telescopes would be good. Other regular telescopes would be good to place on the moon because there's no atmosphere there, so it never rains. And because there's a surface, you can make a really big telescope, which is hard to do in space. And so scientifically and for engineering, I see good reasons to go to the moon. It might also be good, as I've seen pointed out, to build theme parks there. Like if you built a giant dome with air pressure, you could put on a relatively light wings and fly around because the gravity is 6 times smaller. And I could imagine rich people would enjoy the joyride of spending a place where gravity is 6 times weaker. You'd go from weighing 200 pounds to 30 pounds.
That's pretty cool.
And blackjack and hookers.
Well, thanks very much for coming on the show with us and letting
you.
us do the interview. And we're going to take a quick break and we're going to get to the quizzes. Thanks very much.
Everybody get up, it's time to slam now. We got the real jam going down. Welcome to the Space Jam. Here's your chance, do your dance at the
We couldn't
Space
resist.
Yeah, you gotta put the Space Jam theme song. Pretty glad we got away with that.
Yep. So, Richie?
I have a pretty fun quiz for you guys.
All right.
Maybe this episode has been brain heavy, so take a break for a bit.
Okay.
And in honor of how nerdy we're all being right now, this quiz is called Star Trek, Star Wars, or Nonsense. So I'll give you some terminology from either Star Trek, Star Wars, or something I made up, and I'll go back and forth between you two, and you tell me either wars, Trek, or nonsense, and we'll see who can accumulate the most points.
Uh-oh.
Okay, starting with the astrophysicist. This one's easy. Han Solo.
Star Wars.
Right. Nate. Klingon.
Star Trek.
Nice. Astrophysicist. Newtonian shield.
Nonsense.
Nice.
Nice.
Very good, very good. Nate. Chewbacca.
Star Wars.
Nice. David. Lightsaber.
Star Wars.
Very good. Nate. Vulcan.
Star Trek.
Nice. David. Launchpad.
Star Wars.
Ooh, I got that as nonsense.
Oh.
Launchpad?
I guess you can
think
kind of
that's the
say
real
that there
thing.
is a launch pad, but they don't really say launch pad.
Okay.
I made that one up. Nate, phaser.
Star Trek.
Yes. David, Wookiee.
Star Wars.
Yes. Nate, tractor beam.
Star Trek.
Yes.
Also Star Wars, though.
Oh, yeah?
Yep.
I don't remember a tractor beam from Star Wars.
-1 for Richard.
I lose a point.
Yep.
David, Alderaan.
Star Wars.
Damn it. Nate, Enterprise.
Star Trek.
David, Hexabeam.
Nonsense.
Damn it. Nate, Jabba the Hutt.
Star Wars.
David, Ensign.
Star Trek.
Yes. Nate, Ectograph.
Nonsense.
Can't get you guys. Dave, Shuttlecraft.
Star Trek.
Yes. Nate, Tricorder.
Nonsense.
No, Star Trek.
Oh,
yes,
no.
finally.
Oh, no.
David, Jar Jar Binks.
Star Wars.
Yes.
Nonsense.
Yeah, I guess so. Nate, Sith.
Star Wars.
Yes. David, Doppler missile.
Nonsense.
Yes. Nate, Uhura.
Star Trek.
Yes. David, Tachyon beam.
Star Trek.
Yes. Ooh, you thought that was nonsense for a second, right?
I wasn't sure.
Nate, Dagobah.
Dagobah? That's Star Wars.
Yeah. David, Admiral Akbar.
Star Wars.
Yes. All right. The winner is David by 1 point.
Oh, it's okay.
Oof.
You can have
you
this
guys
one.
killed that though. That was That was a nerdgasm.
Okay. So
You're
I also
scaring
have a
all the
quiz.
viewers away.
What viewers?
All 5 of them.
Listeners, yeah.
So I also have a quiz, and it's about life imitating art. So real life inventions that are inspired or at least really similar to anything from science fiction. So researchers in the UK have created a device that uses ultrasonic pulses through crystals to move cells. That was based on what technology?
Ultrasonic pulses through crystals.
I think that's from Star Trek, the warp engines.
No.
Didn't they use lithium crystals or something?
Lithium ions.
Damn.
But I think those are real.
I don't know.
It's a sonic screwdriver from Doctor Who.
Oh.
I'm not a Doctor Who guy. Yet.
Okay.
Not yet.
Jules Verne's Clipper of the Clouds later inspired the invention of what?
Clipper of the airplane? The
No.
helicopter?
Helicopter. There
Alright.
you go.
Ooh.
It's
Okay.
1-0.
I think Leonardo da Vinci thought of building helicopters. It didn't work out, but he had pictures.
Yeah, but they were more spiral
Uh-huh.
built on top and less blades. In Fahrenheit 451, I'll read you a quote from it. And in her ears the little seashells, the thimble radios temp tight, an electronic ocean of sound, of music, of talk, and of music, and of talk coming in on the shore of her unsleeping mind. That was a prediction of the invention of what?
Cell phone?
David?
Earphones?
Earbuds. Yeah.
All right.
There you go.
All right. 2-0.
So the Star Trek food replicator, is that real? Or is it not?
Well, a 3D printer is kind of getting there, I'll say.
Yeah, actually, the Foodini is a food printer that's printing food.
In 3D.
Yeah,
There's those new soda vending machines where you could pick any of 200 sodas.
Oh my god,
Whoa.
I'm so excited. And you can mix them too.
It
I
kind
wish
of
they
looks
had
like
them
a
here.
replicator.
Earl Grey, hot.
The Sigmo translator, which is a device that connects via Bluetooth to a smartphone, is based on what? Sorry, it's a translator.
The universal translator in Star Trek.
No, isn't it from the fish from Hitchhiker's Guide to the Galaxy?
The Babelfish.
Oh.
The Babelfish. Mark Twain's telectroscope would later be a prediction of what? He later called it the limitless distance telephone and said that it could broadcast text and images as well.
So I guess that's a cell phone.
I don't know.
It's tough. It's the internet. He wrote all about it without knowing anything about the internet, obviously.
I was thinking of like that satellite phone from Lost.
And watch Lost. The Argonaut was the first of its kind, first used in 1898, and was inspired by a Jules Verne novel.
Argonaut?
The Argonaut.
First of its kind in 18... Somebody went underwater?
Nice. It was a submarine. It was the first submarine to operate independently in the open ocean.
Oh.
And actually, after its voyage, the inventors received congratulatory letters from Mark Twain.
Oh.
I have one more question.
Alrighty.
So in 1942, this is a tough one, Robert Heinlein published a short story about a physically infirm inventor named Waldo. Today, Waldos are used in the nuclear industry. What are they?
So what I'm visualizing is not correct. I'm saying Homer Simpson at the nuclear power plant, and I'm pretty sure that's not the answer.
Imagine that was just the answer. That would have been a crazy question.
No, what's a Waldo?
A Waldo is a mechanically controlled arm
Oh.
used to manipulate radioactive things.
All right. Oh, that is like Homer Simpson. Doesn't he have that? Well, he has that thing that he puts his arms through.
Oh, no. It's not the same. A Waldo is...
It's like a fume hood.
It's mechanically operated.
Oh, okay.
Yeah, and they're still called that today, which I thought was really cool.
Cool. I like how science fiction influences real scientific progress.
Yeah, I mean,
sometimes.
the big example that everyone normally uses is the flip phone, which came from...
Star Trek.
Yes.
Yeah, it's like the
The communi-
tricorders.
Mhm.
I have a question actually regarding, speaking of Star Trek and the time that we have, the warp engines, I guess they sort of warp space-time and they make shortcuts to go faster than the speed of light. Is that possible, hypothetically?
We don't know if it's possible. There are people who write down equations that say it could work, but you would need certain kinds of fuel that aren't known to exist. So there's something called the Alcubierre drive, for example, which that math is a bit beyond my pay scale, but it looks like that could work if you get some negative energy fuel. Is there such a thing as negative energy fuel? So far, we haven't discovered it. Maybe we'll discover it one day. In terms of technology, in terms of things that exist that are known to exist now, it's impossible to do that.
Okay.
So, David, are you a big science fiction fan?
Yeah, somewhat.
So, of all the really cool stuff that's been invented for science fiction, what's the one thing you wish you could have?
Oh, that's a tough call.
Yeah.
Maybe a time machine, or maybe that healing thing that in the movie Elysium that came out 6 months. There's these pods that you go in for 5 minutes and it heals you of all your medical problems. That seems like it would be very useful.
Yeah, that's pretty cool.
But there's ethical implications that we don't have time to go into. But
I would think about those after I got the pod.
yeah, give me the pod first.
Yeah.
Oh, I actually haven't seen it yet.
There's a pod. Spoiler alert.
No, I can't see it anyway. So, is there technology that's coming from science fiction that you think would be cool and you think would be more possible to recreate?
That is... I'm not thinking of anything off the top of my head right now, but I'm sure that there are things coming in.
I think my brother
the
would
time.
kill me if I didn't ask you if it were theoretically possible to have a lightsaber.
The way lightsabers are in the movie, I don't think it's possible. I mean, you could kind of visualize them as being a sword where you raise the temperature of the sword at an instant moment so that it has a pretty color.
Okay.
But that's not quite a lightsaber.
Wouldn't it melt though?
Some metals have relatively higher melting temperatures. So, yeah.
Okay, well, he'll be devastated. Thank you.
All right, so we're running out of time, but
That's
I
it
hope
for
you
the show.
enjoyed learning about space and fire swords and Star Trek and nerding it up overall.
Yeah, thank you so much, David,
Yeah,
for coming on the
thanks
show.
for coming on the
Thank
show.
you for
It's been a great
having me.
time. Tune in next week. We'll be around. Thanks very much.